Hi, thanks. So, yeah, my name is Edward Kent. I work at AutoTrader in the data engineering squad. And today I'm going to be talking to you about how we launched a new ML model using some tools including MLeap and Kubernetes, and how that was different to how we've previously done things. So first of all, just a quick introduction to AutoTrader. If you're from the UK, you've probably heard of us. If you're not, then you probably haven't. So we describe ourselves as the UK's largest digital automotive marketplace. So we're a platform for people who are buying and selling cars to connect. So just a screenshot there of our sort of typical search journey for a used car. And while we're now a fully digital business, our history is quite interesting. So we launched back in the 70s as a print operation. So we had a number of print magazines across the country. And we launched our first website in 1996. So just for some context, that was 2 years before Google was founded. And then over the years, kind of the importance of the digital site grew more and more. And in 2007, our digital revenue matched print for the first time. And then in 2013, we made the strategic decision to go entirely digital and to cut our print operation entirely. So just some kind of stats there on our consumer site. For me, kind of the standout figure there is the 4 times more automotive searches than Google. It's limited to the UK, but still I think it's quite a powerful statistic, just showing the kind of traffic volumes we get. And the sorts of services we provide. So if you're a consumer looking to buy a car, we're most well known for our new and used car search listings, but we provide a whole bunch of other tools as well to make that process easier, including valuations and price indicators to give confidence that the car you're looking to buy is well priced. What you're probably not familiar with, though, is the sort of services we offer for retailers. So in addition to the classified adverts, we've got a number of tools, including things like valuations and forecourt management tools that help dealers maximize their profit and turnover. And for me, these are the really interesting ones because they're powered by the data that we collect ourselves. So there's a huge opportunity in that space for machine learning models. So just a quick introduction into how we're using data at AutoTrader. Over the last 2 years or so, we've built up a data platform centered around an S3-backed data lake. Going into that lake, we've got data from various operational databases across the business. That's typically brought in batch using a tool called Scoop. We've got streaming data on Kafka. We serialize that using Kafka Connect. And then we've got all sorts of other external partners who deposit data into the lake directly themselves. Consuming that data, we've got analytics consumers. So those are our data scientists and our data analysts. They are using Databricks notebooks to do sort of interactive analysis. And then sort of separated from that, we've got our production workloads. So on that, we're using Spark and Amazon's EMR, and using a tool called MLflow to schedule jobs. Those production workloads tend to read data from the lake and then write data back out to the lake. They can trigger Scoop jobs to then push it back into operational databases, or they can produce directly onto Kafka. So the model I'm going to be talking about today is called Days to Sell. And this does sort of exactly what it says on the tin. It's a prediction for a retailer who's looking to sell a car, kind of showing them how well they price the car and how that impacts on how quickly it's going to sell. And this metric is being launched in a new forecourt management tool that's due to go live in December. And here's just a screenshot from that. You can see typically the dealer, they would put some information in about the car, so the license plate and the mileage. We can then look up things like the make, the model, attributes about the car, as well as its age, and return back metrics, including our valuations, and you can see there the days to sell metric, assuming the dealer has priced it according to how we think it's valued. So when we think about modeling, I like to think of modeling, kind of launching a new model tends to happen in 2 phases. There's a discovery phase, which is where the data scientists kind of experiment. They maybe bring together different data sets, experiment with different features. This typically happens in a notebooking environment where you can make quick iterations and get very fast feedback on the impact of the changes that you're making. The caveat to that is that the sorts of predictions you can do in that environment are typically limited in scope, and it's very hard to apply the model outside of that notebook environment. And then moving on from there, you've got this production phase. And the key thing there is that in the production phase, everything should be automated. So model retraining and model deployment should be automated. So to help with that automation, it's nice to be able to do things like run tests against our code, acceptance tests against the data it produces, so that we can be confident that things are working correctly. And if something does go wrong, we want our application to be more resilient so that it can maybe self-correct, rerun parts of the job that have failed. The other thing about the production phase is that the sorts of predictions it produces tend to be low latency and be able to be served out to systems across the business in real time. And the caveat to that is that doing experiments in the production phase is typically quite difficult. If you make a change, then measuring the impact of that change can be quite a slow, laborious process. And I said that we've got data-driven products already, things like our used car valuations. Typically, we've found that getting an idea from discovery into production is quite slow and is quite a difficult process. So when we launched this new data to solve model, we did things a little bit differently. And that's what I'm going to be talking to you about today. So firstly, the discovery phase. So using Databricks notebooks, our data scientists worked to define a Spark ML pipeline. So in very simple terms, the Spark ML pipeline is made up of two types of operators. There's transformers that take a data frame and return another data frame. So for example, that could be a data frame containing some text data in a column, and then it returns another data frame containing some extracted features from that text in an array. Just an example. In addition to that, you've got estimators. So estimators take a data frame and in turn return a transformer, which is something that takes a data frame and returns back a data frame. So estimators can be things like linear predictors, logistic regression models, etc. So you define a pipeline by chaining together transformers and estimators. That pipeline makes available a fit method, which you feed in some training data. That returns out a fitted pipeline model. The pipeline model then has a transform method, which you can feed data coming in, and that's what produces your predictions coming out the end of it. So the data to solve model, I'm not going to go into the exact details of how it works, but first of all, we have to assemble some training data, and that training data contains things like historic advert data. You saw we've got visibility of about 450,000 vehicles at any one time. Every single day on the UK market, there's about 20,000 vehicles being added or removed, so that data is constantly shifting. Vehicle taxonomy, so that's data about the types of vehicle that are available on the market. So the make, the model, the fuel type, the transmission type, etc., down to the trim level. And I think it's quite surprising that there's a huge variety of different combinations of that. So currently in the UK market, I think it's something in the region of 50,000 different types of vehicle derivative available. So we also feed in our valuation data, so how well priced that historic stock was when it was sold. And finally, geographic data, so just where in the country these vehicles are located. So that goes into our pipeline. We fit the model using that data to get this fitted pipeline model. And then we have this transform method. So that transform method, you feed in information about the make and the model of the car, its age, its valuation, and its location. And out the end pops the data to solve prediction. So that's the discovery phase, and our data scientists use Databricks notebooks for that. So having defined this ML pipeline, we had to take it into production. And to do that, the first thing we did was effectively take it from a notebook form and rewrite it as a self-contained Spark job that could be compiled down to a single jar artifact. That self-contained Spark job can then be triggered by our scheduler, Airflow. And the reason we did that is a couple of reasons, actually. Firstly, having it as a self-contained kind of piece of code means that we can run automated tests on it. We can write integration tests, acceptance tests on the sorts of data that come out the end of it. With Airflow, we get nice integration with our monitoring and alerting tools. So we use Prometheus and Alert Manager to tell us if something has gone wrong, meaning that we can make a change if we need to, and then kind of take action if it's necessary. And a final advantage is that this kind of gives us an extra stage of code review almost. So taking code that's been written by a data scientist, passing it over to a data engineer who's then putting this into production. If the data engineer has questions, they can go back to the data scientist and they can make sure that they're both understanding the model, and that helps to kind of transfer knowledge about how this model works across the team. So that's actually quite important as well. So Airflow has this concept called a DAG, a directed acyclic graph. So a DAG basically just lets us put together tasks and define the dependencies and relationships between these tasks. So in this case, we've got a task to submit the Spark job that produces the training data. That task, in turn, is dependent on some kind of other data being there in the lake. So we've got the historic advert data, we've got the taxonomy data. This task won't be triggered until that data is all in place. Once that's produced, we trigger a Spark job to run some integrity checks against the data to make sure that it looks correct. And we compare it to the previous run of the model just to say, are the volumes of data correct? Are they broadly in line with what we've seen before? And then finally, we submit a Spark job to actually train the ML pipeline and run some tests against that fitted pipeline. Once that's done, we write the pipeline out to S3. So Spark has native support for serializing an ML pipeline, and we write that straight to S3. So that's how we train the model. We've then got to deploy it. So just to sort of set the scene about how we currently distribute metrics across our services, we've got this metric aggregator service. This is a web service that sits in front of a bunch of smaller microservices. So those microservices provide things like vehicle valuations or price indicator flags for a vehicle where we pass in things like the make, the model, the age, the mileage, and its location. Talking to that metric aggregator service, we've got our front-end apps. So those are the dealer forecourt management tools. Also our consumer website. Consumers looking to buy a car can go straight onto our website and get a valuation for the car perhaps they're looking to trade in. We've got third-party APIs, so auction companies, fleet and lease companies, and manufacturers connect to us directly to get these metrics. And then we've got a stream processor. So this is Kafka, and that's used to integrate these metrics into our search index. So it made a lot of sense that this new data to sell metric should sit in the same architecture as a small microservice and to be distributed to the rest of the organization through this metric aggregator service. So we needed to write a microservice. And this is the first attempt we made at it, which actually the slide should probably be titled How Not to Do Things. Effectively, what we did was we took our serialized ML pipeline, got a local Spark context. So Spark can run in local mode on a single machine. It doesn't have to run in a cluster. And we used that local Spark context to read in that ML pipeline. We then have a transform method. So every HTTP request that comes in, we run transform, get the prediction, and put it in a response. And we used Spring Boot to write that microservice. And technically, it worked. It did what we wanted it to, but it was really slow. We found typical response times in the region of about 500 milliseconds, which may not sound too bad, but for a consumer-facing front-end app, it's not quick enough. And with our stream processor, we needed to get the sort of throughput to process millions of messages a day. So this solution wasn't good enough. So the second attempt was more successful, and we used a technology here called MLeap. So MLeap provide a runtime that's specifically designed to serve low latency predictions from an ML pipeline. The only caveat is that you have to take your ML pipeline and convert it into MLeap's custom format before you can use it. So we took our serialized ML pipeline, converted it to MLeap, and then used an MLeap runtime running in our microservice. That provides a transform method that works just like Spark's transform method. And then as the HTTP requests come in, we were able to generate those predictions and serve them out in the response. And this was much more scalable. It handled concurrency much better, as well as being vastly lower latency. So we saw response times drop from around 500 milliseconds with Spark down to about 30 milliseconds with MLeap. So going back to the Airflow DAG, we had a task to train the pipeline and write it out to S3. We then added a final task just to convert the model to MLeap and then write that back out to S3 as well. So that's how our service worked. We then had to think about deployment. So to trigger a deployment, we added yet another task to that DAG, and that's to make a Git commit to the repository that holds the service. And that Git commit just triggers a redeployment. So we say the model has moved. This is where on S3 it lives, and then that redeploys the service. And deploying the service is really no different to any other service now. It's just it's a microservice, and in AutoTrader, we're moving to containerized deployments. So we've got to build the container. So the first thing we have to do is go to S3 and fetch that MLeap model, then build the app and run some tests. And that works just as it does any other web service in our organization. There's nothing special about it just because it's a machine learning prediction model. So you'll note I said something about testing. One thing we found was writing tests for this sort of service was a little bit tricky. So typically when testing, we can write unit tests and we can write integration tests. Unit tests are used to reason about the code that we've written, and they're no different. We write unit tests for this in exactly the same way, but integration tests pose a little bit of a problem. So typically to do integration tests, you feed the service some known request. The service gives you a response, and you check that the response looks like you expect it to. And that's all well and good for a sort of static service, but in this case, we're retraining this model regularly. And actually, it's difficult to know if the numbers it's giving out are correct or not. So we added an extra stage to the model training process. When we trained the model, we used it to generate some sample data. So the input to the model and the prediction that model was producing. And we saved that sample data to S3 alongside the model. So when it came to running these tests, all we had to do is reload that sample data, and we can use that in the integration tests. We know what the input should be. We pass it through the service, and we know what the output should look like. So we can do reasoning like that and check that the numbers being produced by our service are actually correct, not just that it conforms to the correct schema. So, like I say, containerized deployments using Docker. The final stage of that deploy pipeline is just to publish the container to our container registry. And that deployment process, I think I said it before, but I'd like to emphasize, is really no different to any other application, web service application in our business. And we've got hundreds of these doing all sorts of different things. So publishing the container, then the final piece of the puzzle is to deploy it. So Kubernetes is what we're using for deployments. And if you go to Kubernetes and look at how it describes itself, they say this. They say, Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications, which is all well and good. In practice, what that means for us is it's basically an automated runtime for deploying Docker containers. And it handles all sorts of things like scaling, repair. So if an instance of our container has a problem, it can automatically kill them off and regenerate them. It provides tools like load balancing, monitoring, alerting, etc., all out the box. So this is what we're using for containerized deployments across the business. And in very, very simple terms, what it looks like is this. We've got this concept called a pod, which encapsulates one or more containers. Kubernetes deploys these pods behind a load balancer, and then when we want to serve out requests, we talk to the load balancer. The load balancer ships that request off to one of those pods, and inside that pod is our container serving out the model. And just to kind of tie it all together, that's what it all looks like. So having published to the container registry, we trigger a Kubernetes deployment, just as we would any other service. So that's what it looks like. So just to kind of go through it one final time, we've got this discovery phase where we're using Databricks notebooks to do experiments, make quick iterations, and get very fast feedback. Having kind of formalized the model using those notebooks, we then take the model into production, firstly by turning it into a self-contained Spark job. That Spark job is triggered using Airflow, our scheduling tool, and it produces some training data. That training data, we run some checks against it to make sure it looks correct. And then we use that training data to train an ML pipeline. Once we've trained the ML pipeline, it's written to S3 and then converted into MLeap. The final stage of that is then to make a Git commit to trigger a redeployment. That redeployment deploys a service using the MLeap runtime and Spring Boot. It's packaged into a container, pushed to our container registry, and deployed using Kubernetes. And if you were at the keynote this morning, you probably saw mention of this, MLflow. So one of the things MLflow purports to kind of solve, one of the pain points it looks to address, is this process of saving models and serving them out in real time. So it's sort of still a work in progress. One thing MLflow does support now is export of model to MLeap format, but we think probably there's going to be a bunch of stuff coming here in this space that could probably simplify this process even further. So we'll be looking at this with interest just to see if we can integrate that into our workflow. And that is it, I think, a little bit early for a final session. Thanks.
All right, if you have a question, raise your hand.
Hello. Hi, thank you for a very interesting presentation.
Okay,
you described 2 transformations of the pipeline, and the second one was from a Spark job to an MLeap runtime format. But the first, which apparently is automated, is that correct?
Yes.
But the first one you described was after the Python notebook's been written, it gets rewritten in Spark.
Yes.
And is that a manual process?
Yeah, so I say rewrite, it's more of a port. We didn't, so we took the notebooks that our data scientists had written and effectively just transformed them into a self-contained Spark job. Yeah.
My question is that introduces friction in the flow, and it also means that if there's a problem in production, the data scientist might turn around and say, well, hang on a second, I didn't write that. I wrote this. This is a Python notebook. How have you handled it? Has that worked for you?
So in this case, it did. So it wasn't a case of our data scientists give us the notebook and say, right, there you go, and that's it. So we worked very closely with the data scientists to then kind of take that code and build it into the self-contained Spark job. So the data scientists will understand how it works on the production side as well as on the development side.
Okay.
But yeah, it's a good point.
Thank you.
Hi, thanks for the talk. It was great. You mentioned about 30 millisecond response time, which is great. That's the level that we are looking for. But I'm wondering, is MLeap very sensitive to the model or algorithm that data scientists put? If they change the algorithm, is it going to change the response time? Or how sensitive is it to a specific algorithm or model?
So it's probably fair to say the more complex the model is, the higher the response time is going to be. Actually, the biggest issue for us was that MLeap doesn't support the full range of transformers that's available in MLlib. So we had to kind of be a little bit careful to work around that.
More questions?
Hi. Going back to what you just said about MLeap not supporting every transformer in Spark. So, like one of the cases that I ran into is, for example, the SQL transformer from the MLlib. That when you basically anything that you want to convert into MLeap, it will just crash or something, and it will say that it can't convert the pipeline. And the solutions I saw for that are writing custom transformers, both in Spark and in MLeap. So I'm wondering if that's something that you've encountered, and I mean, what were your solutions for? Did you do just that?
So we encountered the exact same issue when I say a transformer wasn't available. It was the SQL transformer. So effectively, we got around it by constructing our ML pipeline actually as 2 pipelines. So one using just the sort of forbidden transformers to prepare the data so it goes into the second pipeline. And then on the service side, as the HTTP request comes in, we transform that request manually using it. So we didn't write it as an MLeap transformer. We just kind of just hand cranked it, I guess. So that's how we got around it.
Questions? Any more questions? Anyone else?
Hello, thank you very much.
Thanks.
First question is about methodology, actually both of them. Firstly, how do you implement your pipelines? Are you putting some, for data preparation process, are you implementing every data preparation step that you have, like filtering, whatever, VERS, SQLs in your pipelines?
No.
No, you still use Spark SQL, right?
So we're still using Spark SQL. So we've got, in our data lake, we've got this concept of kind of raw data and then refined data. So the refined data has already gone through a Spark SQL ETL-like transformation. And the idea is that this data is probably useful for more than just this model. So candidate data sets that we think have value across, in not just this application, but across the business, are made available in that refined data set. And that's where we fed data into this pipeline.
I see. And the second question is, I have a similar case to this one, in a sense. It's like preparing a cross-sectional data in data science terminology. Some of the features might be forecasts about tomorrow. If you know how much cars can be sold tomorrow, you might have more probability to know the days to sell as well. That might be something that changes by market rates, like market trends. Do you have such features in your project like this? And did you use Spark for time series forecasting for that?
So we have, but not for this project. And I think trying to do this stuff maybe just overcomplicates it, and then, frankly, you probably succeed half the time and you fail the other half. I think that's a really complex, difficult thing to be doing. So, no, we didn't. While I'm up here, I'm going to plug as well. We've got an engineering blog, engineering.autotrader.co.uk. So there's a post describing this talk, along with some other cool stuff.
Any other questions? Okay, let's give them another round of applause.